Welcome everyone. Today we are diving into the future of software design by exploring how we can automate software architecture using distributed AI intelligence. Specifically, we will be taking an inside look at the MAAD framework, which stands for Multi-Agent Architecture Design. Imagine an automated, intelligent assembly line, but instead of building machines, it constructs complex, production-ready software architectures. Let's start with the core problem we face today. The architecture bottleneck is severely limiting agile scalability. On one side, engineering teams are crushed by agile pressures, such as the need for rapid iteration, continuous delivery, and shifting business goals. On the exact opposite side, they face massive system complexity driven by competing quality attributes, legacy dependencies, and strict regulatory mandates. Caught in the middle is the architect. Currently, architecture remains a highly manual, time-consuming process heavily reliant on personal, tacit knowledge. This ultimately results in a very limited exploration of alternative designs. You might be wondering, don't we have automation tools for this? The truth is, current automation tools lack architectural domain specificity. Traditional architecture description languages require manual expertise, while single-agent LLMs like standard ChatGPT are prone to hallucinations and isolated reasoning. Even code-centric multi-agent systems, like MetaGPT, are optimized strictly for coding and lack true architecture workflows. That is exactly where the MAAD framework comes in. It is the only complete solution that successfully combines task automation, domain knowledge integration, cross-view consistency, and iterative quality evaluation. So, how does it work? MAAD orchestrates a knowledge-driven architectural pipeline. It takes an ambiguous software requirements specification, or SRS, as its input. This document enters a multi-agent workspace, acting like a robotic assembly line equipped with external knowledge and a dedicated memory bank. What comes out on the other side? Production-ready multi-view blueprints and structured evaluation reports. Essentially, MAAD transitions architecture from an isolated, one-shot guessing game into a continuous, feedback-driven optimization engine. Let's look under the hood at the anatomy of the MAAD framework. The system is powered by knowledge sources, heavily relying on foundation models and both episodic and semantic memory to infuse knowledge. This feeds into the multi-agent workspace where four key AI personas operate in a continuous loop: the analyst, the modeler, the designer, and the evaluator. Through feedback working memory, these agents process the software requirements and output their work into an artifacts pool, generating comprehensive architecture views and documentation. These four specialized agents mirror a professional engineering team perfectly. First, the analyst parses natural language inputs into structured functional, non-functional, and architecturally significant constraints. Next, the modeler selects design patterns and constructs standard 4+1 architectural views from those constraints. Then, the designer synthesizes these models into developer-ready technical specifications, like APIs and deployment schemas. Finally, the evaluator acts as the uncompromising QA gatekeeper, constantly verifying traceability and cross-view consistency. Let's zoom in on the modeler agent for a moment. This agent translates non-functional and architecturally significant requirements directly into standard 4+1 views. This includes the scenario view for use cases, logical view for object states, process view, development view, and physical view for deployment containers. By outputting everything in strict plant UML syntax, the generated models remain both easily human interpretable and rigorously machine verifiable. Now, this is a critical point to understand. MAAD is a feedback-driven optimization engine, not a one-shot generator. After generation, the evaluator performs scenario analysis, traceability mapping, and risk identification. If the architecture doesn't meet the standards, the evaluator rejects it and forces a targeted revision before moving to the next phase. By constantly referencing its hierarchical memory, this uncompromising QA gate prevents AI hallucinations from propagating. But how does the AI know what constitutes a good architecture? We ground the agent's reasoning in authoritative architectural standards. Using Retrieval-Augmented Generation, or RAG, the foundational LLM brain is connected directly to a knowledge vault. This vault contains strict ISO, IEC, and IEEE standards, alongside textbook architectural patterns. This context-aware retrieval bridges the gap between raw LLM capabilities and strict, industry-compliant engineering practices. As MAAD works, it actually learns and gets smarter over time. A hierarchical memory architecture enables cross-task knowledge reuse. At the top, working memory stores the transient context and intermediate artifacts for the active iteration. Below that, episodic memory records historical, task-specific design experiences and revision rounds. Over time, these logs are distilled down into semantic memory, creating a long-term repository of generalized architectural rules, domain expertise, and validated patterns. Of course, we needed to prove this framework works in the real world. We stress-tested MAAD against MetaGPT, the current state-of-the-art multi-agent baseline. We tasked MAAD with generating architectures completely from scratch using 10 highly technical, complex requirements, including systems for the VLA radio telescope and the Mars Express mission. The outputs were judged using rigorous quantitative metrics and qualitative assessments via industry architect interviews. The results were undeniable. MAAD generates structurally superior, lower complexity architectures. Compared to MetaGPT, MAAD achieved a lower coupling degree, meaning higher modularity. It also achieved lower interface complexity with cleaner, explicitly defined contracts, and highly optimized structural complexity. The dedicated evaluator loop and domain knowledge injection consistently produce cohesive architectures that simply outperform general-purpose frameworks. However, we did discover that the foundational LLM ultimately dictates the ceiling of architectural reasoning. During testing, models like OpenAI's GPT 5.2 and Qwen 3.5 achieved consistently superior performance across completeness and architectural quality metrics. Conversely, models like Meta's Llama 3.3 and DeepSeek R1 showed suboptimal performance, as they struggled with the complex, multi-step spatial and logical reasoning required for true architecture design. To summarize, MAAD represents a massive paradigm shift. It is domain-aware, replacing code-first hallucinations with rigorous, standard-compliant modeling. It is feedback-driven, shifting from a single-shot prompt to an evaluated, iterative optimization loop. And it is self-learning, distilling project context into permanent semantic memory for compounding ROI. Ultimately, MAAD lays the groundwork for platforms that deliver rapid, reliable software architectures at scale, allowing human architects to finally focus on high-level strategy rather than manual translation. Thank you for your time.